Welcome to our module about Density Porosity Tool. In this module, we will explore the tool's functionality, applications, logging conditions, and the physics behind its measurements. We'll understand what bulk density is and how it is related with porosity. Finally, we will also learn about the photoelectric factor and its use for determining rock types. Let's start. The primary objective of logging a density porosity tool is to determine formation porosity and lithology. To achieve this, we calculate a formation property called bulk density, and from this, using the following equation, it's possible to derive a value for porosity. With knowledge of porosity and true resistivity from a resistivity log, the fraction of pore space occupied by water, known as water saturation, can be calculated using the Archie equation. Once we know the quantity of water, it will be assumed that any fluid that is not water will be hydrocarbons, and that's how we estimate hydrocarbons saturations. Additional applications of porosity tools include determining shell volume, VSH, when combined with another porosity measurement like neutron porosity tools, identifying gas burn formations, again combined with neutron porosity, estimating hydrocarbon density, and describe rock mechanical properties with data from sonic logs. The density porosity tool is capable of acquiring data in most well conditions, including freshwater-based mud, saltwater-based mud, oil-based mud, air-drilled boreholes, but it cannot provide accurate data in case holes because sensors are generally mounted in a pad that requires permanent contact with the formation to get proper measurements. Now we will cover the physics of the measurement. The density porosity tool uses a radioactive source to emit high energy gamma rays into the formation. These gamma rays interact with the surrounding formation. As these gamma rays undergo multiple collisions against atoms in their formation, they go from high energy levels to low energy levels until they reach a point where some of them are absorbed and cease to exist. But some of them, now with different energy level, do reach the detectors, usually two scintillation crystals. And based on the measurements, the tool calculates two key properties: bulk density and the photoelectric factor. This is useful because with the bulk density, we can calculate formation porosity using this formula, and with the photoelectric factor, we can determine the lithology as shown in the table. It is important to understand that gamma rays emitted from the radioactive source interact with the formation basically in two ways. High energy gamma rays above 100 keV collide with outer shell electrons in the formation, losing energy in a process called compton scattering. This interaction is not dependent on the type of rock, lithology independent. By measuring this scattered gamma rays, we can determine the electron density, and with this compute the bulk density of the formation. Another type of interaction is photoelectric absorption, a phenomenon that occurs when low energy gamma rays below 100 keV interact with the inner shell electrons, losing all their energy. This interaction is dependent of the type of rock, lithology dependent. By analyzing the reduction in gamma ray counts due to photoelectric absorption, we can determine the photoelectric factor, which helps identify the type of rock based on the formation average atomic number. Talking about detectors, density porosity tools have two scintillation detectors, one called long space and other short space. Based on the distances from the radioactive source, they measure the gamma rays that return after interacting with the formation. These detectors contain sodium iodide crystals, which produce light pulses when hit by gamma rays. These light pulses are converted to electrical signals by a photomultiplier tube. allowing us to measure the energy levels of gamma rays. These energy levels are recorded by the tools as count rates. But consider that corrections must be applied on these count rates to compensate for borehole diameter and mud weight, since variations can affect these measurements. Also, corrections for standoff are necessary. Remember that standoff is a separation between the detector and the formation caused by washouts, borehole irregularities, or mud cake. For these corrections, whenever in presence of a density porosity log, look as quality indicator the curve CORP, correction plus, and CORM, correction minus. Please note that the conversion of count rates to bulk density and photoelectric factor is out of the scope of this course, since it depends on the specific tool and each service company. However, it must be noted that the ability to produce accurate values of bulk density and photoelectric factor is guaranteed through calibration. For this, the porosity tool is calibrated at the shop in an aluminum block and a magnesium block, both which have known values of bulk density and photoelectric factor. Once at the well site, a field block made of aluminum is used for field verifications before and after logging the tool in the well. And that's it for this chapter. To recap, we explored the density porosity tool, its key application in determining formation porosity and lithology, the lithology conditions under which it operates effectively. We described the principles of the measurements, discussing gamma ray interactions, energy levels, and the role of scintillation detection. We also cover essential corrections for borehole conditions and the importance of calibration. With these insights, you're now better equipped to understand the density porosity tool in the wireline logging. Thank you.